So my name is Jo Clark and I'll be your host today. I'm going to kick this off by giving a brief introduction to the event, and then I'll hand over to our speakers. So it's clear to us that we need a whole system approach to materials in order to accelerate decarbonisation to net zero. And this runs right from the manufacture of the fundamental materials through to the technologies and the way that they are used and to their eventual end of life. And steel, which is heavily featured in our research, offers a perfect example of the decarbonisation and circularity of materials that is possible. So the projects you've heard from this week and the one that you're hearing from today are well positioned to work across that system, and we're bringing these together in a project called Switch Connect to make our research more accessible in the future. So we've seen a few examples of our research across the system. So Tuesday we heard about the fundamentals of steel manufacture. Yesterday, we heard about the development and use of solar technologies. And finally, today, we'll hear about planning for the end of their useful life. So we'll have a short presentation, and then there will be an opportunity for questions afterwards. So as the presentation continues, please type any questions you have into the Q&A box so we can pick these up at the end. So I'm going to hand over now to Dr. Rhys Charles for an overview of his work on the circular economy and progress made embedding it in the design stages of our photovoltaic research. You'll also hear from Professor Matthew Davies, who can't be with us today, but has pre-recorded his presentation. So over to you, Rhys.
Thank you very much, Jo. Thank you for the kind introduction, and thank you also for the kind invitation to present today. We're really flattered. Matthew's very sorry he couldn't deliver his talk in person today, but you'll see from his recording he's really happy to speak to anybody about any questions you might have about anything, and I'll do my best to answer questions at the end as well. So Matthew is going to talk to you about some of the research our group is doing. What I'd really like to do first, though, is give you some context to why we do what we do and why we approach it the way we do. So I work at the specific IKC, and I work with the solar energy guys there. I'm actually, my background is more in electronic waste management. So what we do together now is try and create technologies which are inherently more compatible with circular economy. So why do we do that? Well, it's all about sustainable development, okay? And sustainable development kind of means different things to different people. So this is the way we kind of view it and try and define it. So most of you will be aware of the general definition of sustainable development, which is development that meets the needs of the present without compromising the needs of future generations to meet their needs. And that development really needs to be propped up on three core pillars, okay? Proper sustainable development will have social value, economic value, and environmental value. Okay, there should be benefits in each of those areas. And if you're missing out on any of those, you're not really doing something that's sustainable. And of course, in the interests of improving standards of living of all people around the world, the UN have set the Sustainable Development Goals. And what you tend to notice when you look through these is actually they're all interconnected, and very much they demonstrate improvements in social value, improvements to our environment, and economic opportunities for people as well. So we're talking about meeting the needs of people, and what does that mean? So one way of thinking about this is, well, what do people need? You know, when they need housing and infrastructure because they need places to live, places to work. Nutrition is important, agricultural stuff. We need mobility, transport, things like that is increasingly important. A whole range of consumables. We need to provide more and more services these days for people, like education, banking. Healthcare is increasingly important. The COVID pandemic brought that home for everybody, I think. And of course, communication technologies are increasingly important in the modern world. And delivering those things requires materials, okay? We've got to make that stuff for people. So how are we looking? Well, what this graph shows us is the global population. By 2050, there's going to be 10 billion people in the world. And so far, we've only managed to provide a suitable level of economic development in these industrialized countries. So we've got a great deal more economic development that's required for these remaining people in the world. But considering now the environmental picture, where has that led us to? Well, one way of looking at it is this. The Earth has these fundamental planetary boundaries, 9 of them. And what this graph essentially does is plots our position against those barriers. So climate change, for example, we talk about climate change. At the moment, we've exceeded our safe operating space for climate change. Okay, we know we're having significant impacts on the planet, and we've exceeded basically the planet's barrier in that regard. Okay, there are other problems that we've got. Novel entities resulting from pollution. Okay, we know now from recent studies that we've smashed that planetary boundary. It's no secret that we're in the midst of the 6th mass extinction. Okay, our biosphere integrity, we have problems with that, and I won't go through all of these, but you can see that the development that we've undergone to date has taken us right to the limit of the planet's ability to sustain us. Another problem we're facing, especially when we're starting to think about delivering technologies that we need and meeting all the needs of people, okay, is that materials that we need to do these things, particularly technologies and so-called critical raw materials, their availability is becoming questionable, okay? There are serious supply risks for the future around some of these things. This is the first European, no, it's not. This is the critical raw materials list from Europe from 2021. And again, what you see coming out of these things is rare earth metals, platinum group metals, a lot of our semiconductor stuff, things that we really need for advanced technologies for the green transition, are all the things that are facing serious supply bottlenecks in the future. That's the list, just to show you what it is. Apart from the technology metals, if you will, we're talking about other things like graphite, really important for lithium-ion batteries for energy storage. In the context of PV, silicon metal, and some of the other semiconductor metals like gallium, indium, all serious risks to future supply, okay? The RSC a few years ago did this work where they looked at, elements in danger. And what they tried to do with this distorted periodic table was show how abundant, first of all, each element is on the Earth. And that's the size of the element represents that. And then color coding it, showing how serious supply risks are within the next 100 years or so. To help bring this home, to show how widely used a lot of these elements are. Anywhere you see a mobile phone, those materials are in your pocket right now, in your phones, in your laptops, all of that stuff. And for a lot of these things, we're looking at serious risk to supply within the next 100 years. So, that's not that long away, and we're going to have to deal with this issue while we're going along the green transition as well. So another way of looking at this, where are we with sustainable development, is like this, okay? What this graph does is it plots positions of countries according to their human development index. So that's a rough measure of standard of living. And against their ecological footprint per person here. That's sort of like per capita impact from your lifestyle. Now, this blue line is the UNDP threshold for high human development. So above that line, everybody's got a pretty good standard of living. So really, we want to get all these countries on this side of the blue line. And these dashed lines represent the Earth's biocapacity to sustain each of us. And as population has grown, obviously, that has shrunk. Now, the problem we see is that as countries become developed, they transition according to this line here, which is a big problem because where we need everybody to be is down there. Because if you're down there, you're living well, but sustainably within the planet's limits. Now, the reason that this has occurred is because most of the economic development, if not all of it, pretty much to date, has been based on linear economic models, okay? What we're doing is we're taking stuff from the ground, we're making it into materials and products, which we then sell. And that's the only point we really generate value from this whole thing, is at the point of sale. Those make their way onto a user who uses them for a while, and then they're disposed of. For the most part, the materials contained will be dissipated or downcycled or lost from the economy altogether through landfill, energy from waste processes, things like that. At each stage, we're consuming fossil fuels for energy, and we're creating a lot of emissions to the atmosphere, but also a lot of waste emissions as well. Because of that, to create this economic development, You just have to keep sending materials down this pipeline, okay? And that's increasingly contributing to our environmental degradation and the criticality of our raw materials. So what we need is a new system, a system that enables everybody that has a suitably high standard of living to reduce their environmental impact massively, but also provide economic development opportunities for these guys, allowing them to increase standards of living, but without exceeding the planet's limits to sustain us. That system is the circular economy. So in a circular economy, at some point, things are mined and made into components and products. But instead of being sold, what we can do then is provide those as a service, lease them or something like that. They make their way to the user. And then what we want to do is retain those products in use for as long as we can. So that means maintenance is important, okay? We need to be able to fix and upgrade stuff. We want to design it for longevity, first of all. But when that product is no longer useful for people, what we want to do is make sure it's collected and redistributed. We want to reuse it. If we can't do that, what we want to do is either refurbish the thing to bring it back into a usable condition, or harvest as much of the original product as possible and use that to make an as-new product and remanufacture it. Only when all that's not possible do we even want to think about recycling. And we absolutely want to minimize leakage of materials from the system, okay? Now, the reason we want to do that is all that impact in the front end of this chain, all of this impact, right? 66% of all emissions are embodied in products, right? They're created in the development of materials, the manufacturing of products, and delivering those products to people. So if we can retain that embedded impact in the tightest loops of these economies, we can start to meet people's needs, but minimizing all the impacts from primary production, okay? Now, also, in order to minimize resource consumption and leakage of materials from the system, eventually, when we can't reuse materials in our own product loops, we should look at industrial symbiosis. Maybe those can become raw materials of other organizations. And likewise, rather than us going for primary raw materials, maybe we can manufacture from secondary raw materials elsewhere in the circular economy. So this is the context to what we do, okay? Now, renewable energy is obviously extremely important in all of this, okay? That's going to decouple our reliance on fossil fuels for economic development. And solar energy is a huge part of this. Looking at biological materials as well, which can go back to nature, is also increasingly important. But solar energy is the area we work in. Now, the emissions reduction potential of circular economy is going to be vital if we're going to hit climate targets, okay? But apart from efficiency savings through things like circular economy, we're going to need to deploy all this renewable energy technology, okay? This is the remap plan for climate change mitigation. There are many plans, but they're very similar, most of them, okay? And you can see that we need to get 86% renewable energy generation by 2050. And the vast majority of that is going to be split between wind and solar, okay? Now, at the moment, 95% of the solar market is dominated by silicon PV, which for my money is not inherently sustainable because of the issues we have when we come to end of life management of this stuff, okay? We can't cycle the materials back in because it's not designed for end of life, okay? In order to enable PV to be utilized effectively at end of life in a circular economy, we need to design it right in the first place. So Matthew's going to talk to you now about the work that we do, mainly with perovskite PV, in order to try and create inherently much more sustainable and circular PV technology. So,
hello everybody, I'm Professor Matthew Davies. Thank you to Rhys for the introduction to circular economy. I'm going to continue the theme, of course, and talk a little bit about our work in ingraining sustainability into emerging renewable energy technologies, and particularly perovskite photovoltaics, and some of the drivers for why we think this is vitally important. So I work at the Specific IKC at Swansea University, and Specific looks to design technologies that generate, store and release energy at the point of use, and has taken this through to build-in scale demonstrators, as can be seen in the picture here with two of our active buildings. So if we take a step back and look at our current scenario, of course we're all very well aware of the problems of global warming, and despite the awareness of these problems, carbon emissions still continue to rise, and they continue to rise about 1.3% annually. This is increasing our need to deploy renewable energy technologies very quickly, and it also lowers our chance of mitigating climate change and certainly of preventing greater than 1.5 degree global temperature rise in the near future. The good news is renewable energy technologies and the cost of renewable energy technologies has declined rapidly. So particularly wind and solar are now cheaper generally globally than fossil fuels, which is fantastic that we've got to this point. And now we have technologies ready to help mitigate climate change, but we need to deploy them very quickly, and we're not deploying them quickly enough. Now, in deploying these technologies very quickly, we're going to need access to lots of materials, technology, metals, and things like that. Okay, so this is our problem historically. What we've done is we've grown our economy, the green line on the graph here, by digging materials out of the ground, by using primary resources. And what this has caused is an enormous amount of carbon to be released into our atmosphere, having obvious consequences. So what we need to do moving forward is decouple our economy from the primary consumption of materials. So basically we need to stop digging materials out of the earth as much as possible, use secondary sources and cycle materials much more, and prevent vast amount of carbon and carbon materials going into the atmosphere. So how are we doing with that? Well, currently not very well. In 2021, 100 gigatons of materials were extracted from the earth. We cycled around 8.6% of those. This is down from 9% a year before. So we're actually going backwards in terms of our material stewardship and efficiency and things like that. And we can't get away from the fact that climate change and material use are very much linked. So if we're going to mitigate climate change, we have to deal with global greenhouse gas emissions released during this extraction, this primary extraction of materials and manufacturing down the line. Another fear, if you like, sorry to be the bearer of bad news, is that our access to critical raw materials may become limited. So we need to deploy these technologies very quickly, particularly wind, solar, low energy lighting, battery technologies, electric vehicles. What we need to do as well is try to reduce our consumption of materials, of course. The problem being that a lot of these technologies share similar elements. They rely on similar chemical elements to work. Now, what we need to avoid is a scenario where they have to compete for those elements. So we need to make sure we design products where we know what goes in is designed for remanufacture and reuse at end of life rather than recycling. So we need to be able to extract these critical raw materials at end of life so we can use them again. This is the periodic table of elements, of course, and what we've done here is highlight the current recycling rates at end of life for some of the critical raw materials, or for all of the critical raw materials. So this is what we're doing at specific and looking to integrate emerging technology into this circular economy. So Rhys has already explained circular economy and this diagram to you, so I won't do that again. We know, of course, that perovskite's a solution processed material that offers potential benefits in terms of dissolution at end of life. So potentially we can wash everything off, recover it if it's environmentally beneficial to do so, and put it back into a new solar device. That's called closed loop recycling, and trying to keep materials within the same technology. What we tend to do at the moment is recycle, and recycle really needs to become our last option for our technologies. What we need to do is design them for end of life so we can efficiently refurbish and remanufacture and put them back into the same products. Where we can't do that, what we need to try to do is develop industrial symbiosis where the waste of one industry becomes a feedstock of another industry. This also addresses another problem, which is our global waste. So we produce vast amount of e-waste, or waste electronics. It's the fastest growing waste stream on the planet, and it has lots of technology, metals and critical raw materials. So we need to recover the technology metals from existing e-waste waste streams and feed them back into our technologies, and we certainly need to design the technologies that we're putting onto the market with circularity in mind, so we can recover and reuse materials at end of life. It's important to note as well, although this needs a shift in design, and by design I mean the design of the module and what that actually looks like, as well as the chemical design of the product to allow some of these things. What this will unlock is enormous amounts of social benefit. So it'll develop jobs in this recycling chain, if you like, where we can remanufacture and then put them back into new products. And if we do this, it creates vast amount of economic benefit to society. So we create jobs and we create money through clever design, and we reuse materials. We really ingrain material stewardship into our products, and we avoid bad news stories about renewable energy technologies being an environmental burden when we need to deploy them as rapidly as we do. The challenges moving forward for perovskites are to really maximise device efficiencies, although of course perovskites are already doing well there and can compete with commercially available silicon photovoltaics. But the more we improve device efficiencies, the better the levelized cost of electricity. We need to improve stability, of course, for perovskites, sustainability, get to large-scale manufacture, and in the specific IKC we have Professor Tristan Watson looking at translating our lab-scale devices to larger-scale modules, and we need to replace toxic materials. So currently perovskites contain lead, which may be problematic, but LCA analysis, although somewhat limited, currently says there's no viable alternative or no better alternative to the lead at the moment, although research of course will continue in looking for alternatives to lead. What we focused on is the replacement of toxic solvents in manufacture. We thought this was the greatest impact we could make, and what we've done is managed to replace DMF with a system that combines 4 solvents, and that gives us tunability also in manufacture. So that's one example how we've helped improve the sustainability. We've also looked at understanding really the stability of devices, or the instability, and particularly the causes and consequences of instability. Part of that has been looking at superoxide formation in perovskites and understanding and mitigating superoxide formation, which is available in this paper here. We also have tried to understand the photoluminescence properties, the fundamentals, if you like, and this also gives us a tool to then understand the remanufacture and recycling. So if we dissolve a perovskite material off, redeposit, use it again, is it fundamentally the same as the first time around, and how many times can we do that before we lose or change fundamental behavior? So that's one thing we're interested in. We've also looked at extracting or highlighting where critical raw materials are in waste electronics, for example, and looked at improving the efficiency of tribromide perovskites that are fundamentally quite stable with organic dyes and things like that. So that's a quick snapshot of some of our research. Sorry, that's very quick, but time is limited. I would just like to highlight some of the work from the Royal Society of Chemistry in highlighting these challenges for decarbonisation and the sort of challenges we face, and I would invite you to look at this report which myself and Rhys have contributed towards from the RSC. We need to deploy technologies very quickly. We need to try to ingrain sustainability in these technologies as much as we can, particularly for emerging technologies where we have greater scope to look at design and optimization for a circular economy. We can plan for retention of materials through efficient remanufacturing processes. This will also help us avoid contributing to the increase in scale of global waste. The growth in the electronics PV sector, but generally, must be decoupled from linear consumption of materials. So we need to stop digging materials out of the earth, as I said, look at waste as a resource and adopt the circular economy. We need to try to eliminate materials that obviously pose a risk to human health and the environment, and help job creation and that of a sustainable industry. So I'll stop there. I'd just like to thank my team in particular and my collaborators, and thank you to the EPSRC for putting on this net zero event, and I hope you all enjoyed. Of course, I'm not there to answer questions, and I apologise for that, but if you are interested in anything I've presented, feel free to drop me an email and I'll get back to you. Thank you very much.
Of some of the work we're involved in, and for the sake of time then, I guess I'll take any questions that anybody might have. Thank you for your attention as well.
Yeah, thanks, Rhys. It was really fascinating, great insight into your work, and great to hear from Matthew as well. And I think it's a nice way to conclude our series of webinars. As you said, we are a little short of time, and I can't see any questions in the Q&A. I just wondered, one question I had, Matthew mentioned that, looking to recycle some of the materials from perovskites, see if they can be reused in other cells. What are the most important materials from perovskites that to try and retain at the end of their life?
That's a really interesting question. From an environmental point of view, lead is obviously important to catch, although they're only tiny amounts, and the impact from a single cell probably wouldn't be huge. I mean, people have looked at it, they think it may not even be a massive problem. Any lead you do find in the environment is there because humans did something to put it there. So you're looking at contributing to an accumulation which will not go away. So lead is important to control, and that will be important for faith in the technology as well. But if we're talking about retention of embedded costs and impacts in successive product generations, then the substrates are actually quite important, particularly if they're glass. A lot of embodied energy and impacts go into making that glass. So if we can reuse that substrate by recoating it, that's good as well. There are critical materials issues around some of the transparent conductive oxides we use, but certainly the two lower hanging fruit are the lead and the glass retention. That would be huge in terms of the overall picture.
Okay, thanks. And are we reusing the glass and silicon from existing solar cells or not at the moment?
No. So this is the thing. It's a bit of a dichotomy. Okay. So when people design solar technology today, obviously they want it to last as long as possible. It generates more energy that way, right? So you encapsulate it with EVA. It's like you glue the whole thing together. What that means is when you come to end of life, you haven't got too many options for opening that up and harvesting materials. Okay. So you get the frame off and then people shred it up and then you use mechanical separation. So what you end up with in the end is the silicon and the glass all kind of bashed up in a single fraction, which means it's low grade, it's cross-contaminated, and it'll be downcycled. So we're not really recovering silicon or glass in a way that's suitable for reuse in new PV. So continuing to meet demand necessitates ongoing primary resource development.
Okay, it's quite a problem, isn't it?
It is, yeah.
Thank you. Okay, I can't see any questions popping up in the chat or the Q&A. So it is 11:30, so perhaps we will just call it a day there, and just thank you for your time, Rhys. It was really interesting.
Thank you very much. Thank you for having us, guys.
And thank you all for joining us.